Hey everybody, Mr. Grove here. Today we're going to do a couple of example problems with bridges and seesaws. And so these are problems that involve torque, and torque is going to be part of our rotational motion unit. So let's go ahead and get started. So our first one is going to be a seesaw, a teeter-totter problem. And so we know torque is equal to force times distance, and that distance will be the distance from the force that's applied to the pivot point where we're pivoting from. So in this case, our force that's applied to cause torque on the seesaw would be the force of weight, and then the pivot point would be here in the middle. And so that distance is called the torque arm, and that will be that distance that's in our equation here. So our second condition of rotational equilibrium, and that means all the clockwise torques have to equal all the counterclockwise torques. And so we can set the clockwise torque caused by this person here equal to the counterclockwise torque caused by this person there. And setting those equal to each other then, we can go ahead and solve for that. So torque is force times distance. So our force would be our force of weight on each side, times our distance would be the distance from the person to the pivot point. And so we're in kilograms, so to get weight, kilograms times 9.8 for gravity. But since we're doing that on both sides, we might as well cancel that out. And so you can see that mathematically that cancels and we'll still be left with the same. We could even be in pounds or some unit other than kilograms, and the conversions would mathematically cancel. And so we're in meters on this side, so we come out in meters on this side, and as we solve for x, our answer would be 1.67 meters. And that should make sense because we have a lighter weight person is going to have to sit further away to counteract this heavier person that's sitting closer. Okay, so 1.67 meters would be our answer. Another example is our bridge problems. And so these are kind of classic problems we'll do a lot. And so we have a car and a giant frog here on the bridge. Here's our bridge specifications, mass and length, and we'll assume it's uniform, so the center of mass of the bridge is right there in the center of the length. And our question is, what's the force A and B are pushing up with? So we have two kind of things going on here. The first is going to be just simply the forces being equal to each other. So the up forces equaling the down forces. So our up forces would be the force of pillar A and B equaling the down forces, the weight of the car plus the weight of the bridge plus the weight of the giant frog. Once we do that mathematically, we can solve for those force of weights, and we get the two pillars equal to a total of 54,390 newtons. So that still gives us two variables, and we need to try and solve for that. So anytime you have two variables, try and solve for a second equation, where you can have two variables and two equations and can do some mathematical substitution. So our second equation, we're going to use torques. So that second condition of equilibrium is satisfied. So the clockwise torques are going to equal the counterclockwise torques. And so I chose my pivot point as A, and I would suggest choosing the pivot point as one of your variables, and that way mathematically, when you'll see that it's very helpful down here. So we set up our torques, so we got force of pillar A, force times 0, because the pivot point is at A, plus the torque that's causing a counterclockwise torque as pillar B is pushing up, and that force is times the full length of the bridge. So that's where the 25 comes from. And then on the other side, we have our weights. So we would be creating a clockwise torque for each one of these guys here. So here's the clockwise torque, weight times mass for the car, weight times meters for the car, weight times meters for the bridge, and the weight times the distance in meters for the frog. And those are all set equal to the forces on the other side times their distance for the torques. So once we got our torques, our counterclockwise equal to our clockwise, we can start crunching some numbers and mathematically consolidating things. And then when we solve for the force of pillar B here at the end, we get 25,754.4 newtons. That then can substitute in like we did up here. Okay, and now we can solve for pillar A and we get 28,635.6 newtons. Always ask, does an answer make sense? Well, these add up to this, so that's good. And then B is not as much as A. So does that make sense? Well, we've got a lot more weight. The big frog is closer to the center than what the car is. And so A would make sense that it would be supporting more of the weight. So that is how we do some examples with the seesaw and the bridge problems, and I hope that was helpful.